Welcome back to the classroom. My name is Mr. Wong, and today we'll be looking at Advanced Mechanics, which is Module 5 of the HSC Physics syllabus. We're going to be looking at Inquiry Question 3, Motion in Gravitational Fields. This is the dot point we're going to be focusing on. Okay, so let's move on. Our lesson intention today is to define Newton's law of universal gravitation and determine the force between two mass objects. Your success criteria is to analyze the factors that affect the magnitude of gravitational force and the gravitational field strength. If you need further reading, textbook guidance there. Before we get into the whole concept of Newton's universal law of gravitation, we want to look at this book. So it's called The Philosopher Naturalis Principia Mathematica, or in short, we call it the Principia. It's a very significant book that Isaac Newton wrote. I think he was in between his mid-20s when he wrote it, and that was introducing the concept of the universal law of gravitation, as in all objects with mass will exert a gravitational force onto each other. It also explained the motion of the planets, so it explained why different planets orbit around the sun, and it also explains the concept of why the moons orbit planets. In this process as well, he also invented calculus. Without the invention of calculus, he couldn't actually derive the necessary equations that he wanted to find. So that's what we have. Okay, so we're going to look at how to determine the force of gravity between two objects, this equation here. You might remember the apple and Isaac Newton story. The concept is the apple hit him on the head and he invented gravity. That's not really the case. What he actually related to was the reason in which the apple falls down towards the earth could also be the reason or the same reason why the moon orbits around the earth. And that was the relationship he came up with. The reason why we don't see the effects as strongly comes down to the concept of his third law. So Newton's third law states that any mass object, when they experience a force, they will try and exert a equal but opposite directional force back onto this object. So if we have a look, let's say we have two mass objects. They both exert the same force onto each other, but you can see the vector arrows are both moving in the opposite direction. One is going towards the right, one is going towards the left. So that was his idea of how gravitational force of attraction works. You can see this negative sign here. That's just to represent that it's going in the opposite direction of this first object that we were analyzing. So that's kind of his quick interpretation of the gravitational attraction. What we can actually now look at is what factors come into play when we're talking about gravitational force. So Newton concluded that the size of the gravitational force on any object is inversely proportional to the object's distance from the center of mass, and that is to the square. Okay, so we might just do some notes. Okay, so it's the object's distance square, and it's from the center of mass. So imagine we have, Earth on this side, and we have the sun on this side. We're saying from the center of the Earth here towards the center of the sun here. That is what R represents. So it's inversely proportional to R squared. What that means is if we increase the distance, so if we increase the distance by 2, we actually decrease the force of attraction by 4, or 4/4 of a quarter of the original force. So that's what we're showing. This sign here is what we use to demonstrate that there is a proportionality relationship between the two formulas. He also found that the magnitude of the gravitational force is also related to the mass of two different objects. So if we're looking at the planet and the sun, it'll be this one. So you have big M, which is the larger mass, and little m is the smaller mass. And so he was saying that it was the interaction of two different mass objects that causes this gravitational attraction, which is fair enough because this, again, is the same concept as following Newton's third law. So it follows Newton's third law. Now, if you actually look at this equation here, we have a slight issue, and that is we don't get the units for force, which is in newtons. Now, newtons can be expressed as capital N. If we look at the formula, I'll just get rid of this bit here, I'll rewrite it. If we look at the formula for Newton's second law, which is F equals to ma, then force can also be represented as kilos meters per second squared. So that is how we can express force. But if you look at this scenario we have here, we have kilograms square over meters square. So that's not appropriate for Newton. So he came up with a constant, and that is what we call big G, the universal gravitational constant. It is our way to develop the units for force. So units for force. So it allows us to get the unit for force. It also is an expression of how the gravitational fields are projected in particular space. So units for force. So if we have a look, this is the original scenario we have. G, according to Newton, had the units of N times meters squared over kg squared. So if we look at that, I'll do a different color so it makes it easier. The kg squared cancels out the kg squared, the m square cancels out the m square, and so we're left with n. So that's how we actually end up getting the correct units for force. Otherwise, it wouldn't work. So we can write our formula like so. Sometimes you might see it as a negative, but this is just to express that is an attraction force. So what we mean by that is one object is going in the positive direction and the other object is moving towards it, negative. So attraction. You don't really need to worry about plus or minus because if it's a gravitational attraction, that means that they are moving towards each other. So you can just write attraction. So that's the formula we're dealing with here. Fg, the gravitational force between two mass objects, is equal to G m over 2r, or r2, sorry. So that's how we go there. If we have a look, that means that if we have two mass objects, regardless of the mass, they are going to both experience the same amount of gravitational attraction towards each other. You can see that in our diagram here. You can see as they get closer, or r gets smaller, f gets larger. So this is what we're seeing here. At the same time, they also get larger at the same rate, or they end up at the same value at the end there. So that's what we have. And so here we have the formula to represent the gravitational attraction between two mass objects in space. You can also apply it on Earth, and we'll look at some calculations. So just to remember, Fg is gravitational force in newtons. Big G is the gravitational constant. That's Newton meters squared, kilograms squared inverse, we can see that mass 1, mass 2. So you could write M1, M2, or you could write the convention that we talked about earlier, and that's big M, little m. So that's how you go there. Okay, so let's go to the calculations. All right, so we have Fred and his girlfriend Sue, very much attracted to each other, but by how much? Find the gravitational force attracting them when they are 0.5 meters apart, and do the exact same thing for 2 asteroids of that. So this is relatively straightforward substitution. You already know what the constant is. That's on your data sheet, so please make sure to use your data sheet if you need be. So do our substitution there. You'll find that the overall attraction, if we round it off to 2 sig figs, that Newton's attraction. So 1.2 10 to the power negative 6 newtons. So that's sort of why you don't crash into your friend or your partner or your siblings or your family members, because your gravitational attraction is relatively small. Gravitational force is the weakest of the 4 fundamental forces. So just keep that in mind. If we have a really massive object, so they're in sort of like a billion millions, this is their gravitational force. So again, do your substitution. And we get a approximate attraction force of 618 newtons. Again, attraction. So that's how you do those 2 questions. They're relatively straightforward, so to speak. But as I said, mass or gravitational force is very weak. Now, if we, so to speak, have an example where objects can move at a really fast rate or have a really large gravitational force, this is always the best depiction I always have there. Those who know what this reference is, good for you. If you don't, doesn't matter. Okay, next question we're going to look at is the magnitude of gravitation attraction between the Earth and the Moon and the Earth to the Sun. Now, what I want to show you here before we start is obviously they gave you the numbers in these calculations, but if they don't give it to you in the actual HSC exam, please use the formula sheet or data sheet to help you find the numbers. And even if you do remember what the exact numbers are off by heart, still look at the data sheet before you go into other calculations. Okay, so make sure you use the numbers that's given to you, like so. Okay, so the gravitational attraction, let's do A here, is 6.67 10 to the power of negative 11 times the mass of Earth times the mass of our moon. Okay, divide that by the distance of separation from the center of the 2 celestial objects. You get a gravitational attraction of 1.98 10 to the power of 20 newtons. Again, it is an attraction or attractive. Okay, and then we go to B, so the interaction between Earth and the Sun. So again, do your calculations. Maybe I'll do it in a different color. Hopefully that doesn't confuse anyone. So we have the mass of the Earth, and we also have the mass of the Sun, which is 1.99 10 to the power 30 over the distance in which they're separated from their center. So that gives us a value of approximately 3.2552, sorry, 22 newtons attraction. So you can see there's a stronger attraction towards our sun than the moon has towards us, or vice versa. So that's what you have there. Okay, so that concludes the first part of this lesson where we talk about deriving Newton's law of universal gravitation. In our next part of our lesson, we are going to try and derive the gravitational field near a point mass. So that's what we're going to do next. That's following on this lesson. So I'll see you there. Thank you for listening, and I'll see you in the next one.